Kiskin. He is professor of the Russian Academy of Sciences. In fact, today he presents Kornakov Institute of General and Inorganic Chemistry of the Russian Academy of Sciences. Today, Mikhail is going to speak about approaches to changing the magnetic anisotropy of Cobalt-2 ions in carboxylate complexes. Please, Mikhail.
Yeah, thank you, Viktor Ivановich, for your kind introduction. Yeah, I want to talk today about Cobalt complex, and the first I want to thank organizing committee for this possibility to present our results in MolMag conference after so long break. Not all of us have possibility to visit official city of the conference, so I spent some time of my presentation for short excursion and show some interesting fact about Nizhny Novgorod. The distance between Moscow and Nizhny Novgorod is about 400 kilometers. It will take 4 hours, 6 and more hours by car, or maybe by train, maybe 4 hours. And also it's possible to fly or sail along river. Nizhny Novgorod is situated at the confluence of two rivers, Oka River and Volga River. And this city is a city of big bridges, free road bridge connected to banks, and particular attention should be paid at the Institute architectural monuments, building of past centuries, and the fortress. Yeah, this one. Yeah, this fortress is located on a high bank to protect residents from enemy attacks, which were relevant at past centuries. And the ability of water opened up opportunities for residents for active travel, trade, campaign of conquest. And the city was founded 1221. This year is anniversary of Nizhny Novgorod, 800 years old. The population of the city is about 1.25 million. Maybe you remember that some match of FIFA World Cup in Russia were held in this city. And it is a big city. It has there are subway, and not so far from Lobachevsky, from historical center. You can find Lobachevsky University, and a little bit far away, Institute of Organometallic Chemistry, where our colleagues do perfect and interesting chemistry. And now I want to finish my short, maybe not informative excursion, and I want to begin scientific part of my talk. And today I will talk about cobalt. Why cobalt? It is very impressive metal ion which with free non-zero oxidation state. And cobalt is high spin. It can be placed in different coordination environment with different coordination number. And its magnetic anisotropy, it is very important for realization of single molecule magnet, single ion magnet properties. Depends on its environment, coordination number, and ligand field, and so on. So it's very effective ion for preparation of compounds with unique magnetic properties. And for realization of single ion magnet properties, zero field splitting parameter should be negative. It determines the wall between two stable states. Positive D value also results in no zero out-phase signal in DC experiments, but it comes from either plane magnetic anisotropy with only one stable state. And many papers describe complexes, cobalt complex with positive D value. And sometimes maybe we have some chance to change it locally, but For example, well, what can we use? We can use the synthesis, the design of coordination complexes. We can use different kind of inorganic, organic ligands. On the other side, we can use magnetic dilution. At the first, we use it for isolation of metal centrum from each other to minimize the intermolecular exchange interaction between them. And in some works, have some information about controlling the magnetic characteristics of cobalt ions. For example, this work will show a triangular complex of cobalt with three methyl amide ligands. One of them could be replaced by THF or 3-phenylphosphine, and all of them demonstrate low magnetic relaxation, not zero field, and an increase in electronegative properties of the ligand from nitrogen to phosphorus, and a change on geometry of coordination environment of all these compounds led to decrease in D value like this one, and a certain increase in the magnetization reversal barrier. One more work described tetrahedral complexes of cobalt with phenyl chalcogenate ligands with oxygen, sulfur, selenium donor atoms. All of them demonstrate low magnetic relaxation in zero field, and zero field splitting parameter for all these compounds, for cobalt compounds, is very sensitive to the donor atom of the ligand, as exemplified by significant decrease in D value along an early isostructural series. One more work, also tetrahedral complex of cobalt, where cobalt is surrounded by two collagen ligands and two donor ligands with nitrogen, phosphorus, and arsenic atoms. And the calculation for that compound shows significant decrease in D value with an increase in the electron donor properties of the ligand. And in this presentation, I will talk about the problem of sign switching of the zero field splitting parameter in carboxylate complexes, since the main such complex are shaped with positive D value. And I will start from tetrahedral complexes. This slide shows two types of cobalt complex in which each atoms paramagnetic are surrounded by 3 oxygen atoms of 3 carboxylate groups, so 1 donor atom of neutral ligand, like this one and this one complex. This complex are polynuclear, and cobalt atoms are separated by lanthanide atoms or 2 lithium atoms. Carboxylate groups don't create significant sterical hydrogen, so we can use bulky ligands, and the exchange direction between cobalt atoms are 0 due to so long distance between them, more than 7.5 angstrom. And the choice of ligand, this ligand is follow, it's nitrogen containing ligand, pyridinate derivated 3-phenylphosphine, and carbon ligands like MS1. In this slide, I summarized all data that we have, approximation of magnetic data, teraget spectroscopy, and ab initio calculations, and our attempts to change the sign of D value for complexes with nitrogen-contained ligand were unsuccessful. Yes, you can see this data. And D value for complexes with pyridine and 3-phenylphosphine ligands turn out to be close. They lie in the range of 1828 wave numbers, the use of carbene ligand made it possible to shift the value in the desired direction. But this is about 10 wave numbers and it's still positive. So we propose that the coordination environment in these compounds play roles of wall, great wall that prevents the realization of the goal effect. We have some idea how to change it, how to change the situation, but we haven't realized it yet. One more interesting work was present here, and the authors change substituting this big ligand, a late ligand, and they were successful in the change of D value, zero field splitting parameter from positive to negative. And this work looks like our results where we switch the value by magnetic dilution for mononuclear cobalt complex. Here you can see this complex, cobalt complex in octahedral environment of 4 oxygen atoms of 2 halide carboxylate groups, 2 nitrogen atoms of 2 pyridine amino ligands. On the other side, you can see tetrahedral complex of zinc. Distance, it's tetrahedral as a result of elongation of zinc or distance of 2 halide groups. These compounds are not isostructural. They crystallize in the same space group, but with different cell parameters. We synthesize different compounds with different ratio of metal ions. So the red numbers show that crystals were analyzed by single crystal X-ray analysis. We analyzed the contain, metal ratio, and phase purity. What we see, the first we see the breaking point where we have the transition from cobalt to zinc-rich samples. It is about 50% of cobalt and 50% of zinc. Cell parameters don't change significantly in both series, as you can see. And when we analyze the crystal structure, we observe monotonically increase or decrease some bond late in cobalt-rich samples, and when we have this transition to zinc-rich samples, we see sharp increase of 2 bonds, zinc-O, and some increase in zinc-O and zinc-nitrogen distance. And we have the main question: will we see this effect in magnetic properties of zinc-rich samples, and how we could feel it? Because single crystal data, it is a superposition of many molecules of complex in crystal lattice, but in some case, cobalt complex could be octahedral, still octahedral in zinc-rich samples. So we did some measurements at the first to analyze magnetic properties. Here you can see all of them demonstrate slow magnetic relaxation in non-zero field. Relaxation process for cobalt-rich samples could be taken into account Dirac and Raman process, as you see this curve. And for zinc-rich samples, we should take into account Orbach process too. Yeah, but the data are still enough to analyze the structure of cobalt in crystal lattice of zinc-rich samples. So we did some terahertz spectroscopy. Here you can see two spectra for cobalt complex and zinc-rich sample. Here you can see some differences, energy, delta energy that describe excite doublet for Kramer cyan. Both values are different, and we analyzed many samples. And cobalt-rich samples have the same delta values, and the zinc-rich samples have this one value. And in addition, we did X-band APR spectroscopy, and we observed the same situation. APR spectra for cobalt-rich samples, red lines, and for zinc-rich samples, it's the blue line. They are different, and from this data, we analyzed the sign of zero field splitting parameter. It is possible for cobalt-rich sample and negative for zinc-rich samples. And what we see at the next slide is show calculation data for our compounds, and they are in good agreement with our experimental data, as you see here. And we see some correlation between the distance, zinc O, metal O, and delta value and experimental and calculated delta value. And in this slide, I summarize the second part of my talk. When we use this cobalt complex and two different crystal lattices, we could change the coordination environment of these compounds. It is a result of complementary crystal lattice that includes our cobalt complex and change its coordination environment. But the main cause of this is the level coordination environment of cobalt. It depends on the ligand. And at the end of my talk, I want to thank my colleagues from Russia, from Institute of Tomography Center, from Institute of from Chernobylovka, from Moscow also, from Kyiv, from Germany, UK, and India. Thank you for your attention.
Thank you, Mikhail. Let me see. Yes, I see the question. Clear average.
So that was just an appreciation of the presentation, but I have no particular question.
Okay.
There was a clap. Fan.
Okay. I saw raising hand. So next question from Sergey Vegan. Please, Sergey.
Thank you very much for your presentation. You told us a story when magnetic dilution resulted in changes of the structure of magnetic unit. So, and in your story, it was cobalt as magnetic one and zinc as dilution media. From the chemical point of view, would you imagine another examples of magnetic ions and dilution analogs, which should be considered in the same way, probably? So it should be able to be different in structure, but also should be able to form structural solutions in this case. Thank you.
Yes, it's very interesting question. Thank you. Yes, we try to find such structure because we need a labor coordination environment at the first. Yes, and we need to get, as you told, different crystal structure, maybe. Yeah, but it is not so often to find such compounds. Yeah, and we should taste all of them, for example. Yeah. But because that I think we should found two compounds for cobalt or zinc for iron, for example, and zinc, and analyze the structure. After that, we should do crystals. It is best way, yeah, to find the data from TCDC, for example, or maybe in ULab, your results.
Okay, maybe somebody else. Let me check the list. No more questions. So let me thank you, Mikhail, for your presentation. And now take over for another one.
Thank you.
Our next speaker is Professor Katsuya Inoue. Katsuya Inoue is currently a distinguished professor in Hiroshima University Graduate School of Science, where he studies the properties of molecules that are both chiral and magnetic. For me, it's exceptional privilege to announce Professor Inoue because we are in collaboration for many years. Katsuya, it's your time, please.
Okay, thank you, Victor. Yes, I'm very happy attending here, but I want to visit Nizhny Novgorod again, but sorry, the corona problem. But let's start my talk, and I also thank you very much for the organizing committee to give me a time. Okay, now I start. Then not work. How to? Let's start. Today, I want to talk about the correlation or relationship between the topologically protected object with the chirality problem. Just I want to discuss for everybody this time. Let's start from the history of the topologically object. This is the upper part is first reported in Nature is 2004. This is two kinds of insulators. It's sandwiched, and there is a metallic behavior between the two insulators here. That time nobody know what is happened this system, but there is we can say here is a symmetry breaking for one axis. In the later studies, we found this kind of interface system is coming from the topologically protected object. This is explained for the Dirac cone of the insulator, surface of insulator. Here you can see here is put insulator, but the current is observed by this current is not the normal electric current. This is just spin current. Then people now know this is so-called topological insulator coming from the symmetry breaking of insulator and the vacuum. Then let's consider the spin system. Here is we found in recently almost 10 years ago the chiral spin system. In our system, let's say the right-handed material is the upper side, and the left-handed material is the downside. We already find the helical spin structure inside in the chiral chiral magnet, but this case we have the surface both sides. the spin are pinning by the surface anisotropy. This case, we cannot convert upper state to lower state. It's say, this case is topologically spin ordered state protected by chirality. This is similar thing as you can imagine the Möbius ring. If you make a right twist Möbius ring, and you can make a left twist Möbius ring. The right twist Möbius ring and left twist Möbius ring are never connect, not the same. It's topologically protected. You have to cut them if you change to the topology. Then let's consider from the experimental evidence. I already show many times this sample, then I will go quickly. We are talking about this left side chromium niobium sulfur case. This compound is crystallized in chiral space group. Space group is P6322, and the niobium and sulfur makes a layer, and the chromium intercalated between layers. And the chromium has a spin of 3 over 2, and they make a helix by the Dzyaloshinski-Morian interaction, hole coming from the crystal chirality. And we already know the pitch of helix, and we already observed these properties. This is a Lorentz stem image of this sample. The C-axis is horizontal. And here is a 48 nanometer pitch is correspond to the pitch of the helix. When you look this line, you can find these lines are perfect. There are no branch, no diminishing, and the separate is 48 nanometer is perfect. This means that this spin system is never influenced by the defect of the crystal or magnetic defect or crystal defect. They are never influenced by the these defects. Why? They are so robust, this spin system. This is now we can consider this is just a cartoon of this situation. There are many defects included, but this spin system never influenced by defect. This is so-called topologically protected by chirality. This is the other evidence. This is applying magnetic field perpendicular to helical axis. As you can see this video, the pitch is increasing by increasing magnetic field. Very smoothly. This is this spin system was protected by topology, and the topology coming from chirality. This is a cartoon view. At the zero field, there makes a helix, but if we apply the magnetic field perpendicular to helical axis, the pitch is increasing, and increase, and finally they are going to infinite value. They are smoothly go to the forced ferromagnetic state. But in this situation, we can count the number of this defect. This is soliton. We call it soliton. If we measure the magnet resistance on this sample, helical axis is perpendicular, and we are measuring the resistivity on this side. The red curve is increasing magnetic field, and blue dot is decreasing. As you can see, first, there are many steps found by resistivity, magnetic resistance, and there are many big magnetic hysteresis. If you look more carefully, you can count the number of solitons. This is one soliton, and this one is 2 soliton state, and 3 soliton, 4 soliton. The overall is thousands and several tens million steps. You can count. This case, yes, this is just cartoon view. And you also find in the magnetization step. This is a field dependence of magnetization. As you can see, there is a step. And this step corresponds to the one soliton. But anyway, this system are topologically protected, and there are no influence by any defect, and we can change smoothly this helical magnetic order to ferromagnetic spin order. And this is the total phase diagram. Here is a TC, and this state is paramagnetic, and here is a perimagnetic helix state, and here is a soliton state. There are 2 different soliton states, but finally we are going to ferromagnetic state. The curvature is like this. But yes, and I have to say, the topologically protect means the phase of spin appeared in our world. Normally, the phase never appear to the real space, but if we protect by topology, the phase appeared in the real world. This is 3 of important electromagnetic field. Here is light. Normal light is incoherent, no phase order light. But if we make the coherent phase order light, it's called laser. And for the charge, the normal semiconductor or metals are incoherent phase order. But if we put the coherent charge order state, it is so-called superconductivity. This case, our case is a spin. But normal ferromagnetism or anti-ferromagnet or any normal magnet is an incoherent phase order. But if we protect by chirality, they are going to the topologically protected chiral spin order. This is similar with the superconductivity or laser. This is one of the important property of topologically protected matter. But we already get the evidence by experimental. There are several series we can consider about the topologically protected matter. This is our case. I said before, this case is a helical axis is only one axis. This is P63 axis. The soliton is located in the plate, just perpendicular to helical axis. But there are several chiral magnets already found in the P213 space group. This is manganese suicide or iron germanate. There are 4 helical axes. If we cut the SIM plate on this sample, finally we have the 3 helical axes. This case, soliton running in the 120 degrees to each other. Then if we we can get this Skyrmion lattice. If consider the monoaxial or uniaxial chiral magnet, they can generate soliton, one-dimensional soliton like this. But if we make this 2-dimensional object, in the chiral magnet, we can make a skyrmion state. But more higher three-dimensional object also possible by the mathematically. This is so-called Hopfion. Hopfion is very recently found by the Ivan Smaryuk by on the chiral liquid crystal phase. But nobody found in the magnetic system. And these solitons, topologically protected objects, they have the repulsive force to each other. Then they make us lattice. This is soliton lattice. This is skyrmion lattice. These are Hopfion lattice. This is only one case is possible, but our magnet, molecule-based magnet, there are, we can prepare many different systems. Then now, very recently, we made this kind of magnet. This is three-dimensional, and the manganese holomate system, photography like this. And these are people who are doing, there are several Russian students out there. And the structure is like this. This is a bit busy, then let's go further. This is an X-ray structure on this sample. The important thing is space group is P632. This is chiral, and this space group is same with the previous one, chromium, niobium, sulfur. Let's see, compare with them. Here is a new sample, molecule-based one. And here is, I explained previously, chromium, niobium, sulfur. Space group are same. And the position of magnetic ions, this is for this one is manganese 2 plus, this one is a chromium 3 plus. The position is same. Then look, let's measure the magnetic property. This is a single crystal measurement on this sample. The Tn is 8 Kelvin, and the red is parallel to helical axis, and the blue is perpendicular to helical axis. If we look this one, the chi and the temperature, this is a very typical antiferromagnet for C direction. And let's measure the more detail. This is the field dependence of magnetization at a very low field. This is parallel to C. This is magnetic field applied to parallel to helical axis. This is perpendicular to helical axis. As you can see, this below TC is 8 Kelvin, Tn is 8 Kelvin. Below TL, you can find some anomalies in magnetization curve. There is some possibility magnetic anisotropy or with spin flop or spin flip or something. If we measure that this is AC magnetic susceptibility on this anomaly, yes, here is a low field. You can find this here is Tn. They are going to antiferromagnet. And if increase the magnetic field, you can find here is Tn, but you can find the additional anomalies here. If increase the magnetic field, this temperature is going increasing, and finally is disappear. If we put this is chi double M double prime case, you can find very clearly. You can put the phase on the phase diagram. Line is coming like this. Here is magnetic phase 1. This is magnetic phase 2, and here is paramagnetic phase. This is the field dependence of AC magnetization. if we change the field by the isothermal temperature, you can find anomalies below Tm. Yes, here is also the similar. This is chi double prime, and this is field frequency dependence. Here, this anomaly, there are no frequency dependence. Then this is not reflect from the spin dynamics. This is phase transition. Then finally, this is a total phase diagram of this sample. Here is a paramagnetic phase, and Tn is 8 Kelvin, and this axis is magnetic field. This line is I already put before the phase transition between one phase spin ordered phase, the other spin ordered phase. But if we apply the several more than 10 Tesla, it's 15 Tesla, they are going to forced ferromagnetic state. The mystery is this one. This line is, if we remember, we have the peak in the chi prime and the M prime, it's AC susceptibility, and there is a peak M double prime between this phase. This means this borderline is discontinuous borderline. This is phase transition. The curvature is like this. This is downward convex curve. This phase transition line. Let's remember, this is a phase diagram of chromium niobium sulfur. This phase borderline is upward convex. This is completely opposite. And here is a many solitons, and reducing a number of solitons, and reducing, and going one soliton, and here is a 0 soliton. The soliton is changing 0, 1, 2, 3, like this. Then this line is continuous transition. Difference is 1 and 0. It's completely different. But our case is discontinuous transition. Here is a phase transition, not the soliton 0, 1 like continuous transition. What happened? Then we try to calculate Monte Carlo simulation on this sample. This sample, this is a chromium niobium sulfur cation. You can make a helix like this. But this case is anti-ferromagnet phase. Then now we have to put the spin up, down, and they make a helix by Dzyaloshinskii-Moriha interaction. Then calculation is clearly shown. This is phase diagram. Here is a paramagnetic phase, and Tn is here, and here is some, we don't know what is this, but there is some phase here. And here is a attractive soliton phase. The soliton, they have the attractive force to each other. It's a completely opposite of the repulsive of chiral spin soliton lattice. And here is a repulsive soliton phase. And then this boundary becomes discontinuous in the attractive soliton phase. Why? This is just, if we look, the normal ferromagnetic one, between solitons, they are repulsive force. Then they are going to chiral spin soliton lattice. But this new case, between solitons, they have the attractive force. Then soliton is getting together and the phase is separate. Here is soliton phase, and here is a no soliton phase. This case, as you can see, like ice and water. Here is ice, and water exists at the same time. Ice and water is a first order transition and a discontinuous transition. Then this case is correspond to discontinuous transition or first order, or phase separation occurs just between changing the transition. Now, and then we clearly know here is a very special, but only the anti-ferromagnetic case appear attractive soliton phase. Then this borderline becomes a first order like discontinuous transition borderline. And here is again the same with the continuous transition by the soliton lattice and the forced ferromagnetic. And here is the other mystery, but here is some anomaly we already find in the neutron diffraction, but very like a nematic state. But we call the non-soliton state. Then curvature is also changing, and the nature is already maybe correct. But we want to say, I want to say for you, the molecular spin system. We can design the material. We can design the spin structure also. Then physicist is almost impossible to prepare the new sample, but chemist can prepare the different system. And the different system shows completely different properties from the previous one. These are our group, the center of the Chiral International or Research Center. We are collaborating with Russia in the UK and the United States. And they're supported by these funds from Japan, the UK, and the Russia. And here my group. Here is no Russian person. Sorry. But we now have a group with almost 250 members within all world. Then thank you very much. And if you want to know more detailed results, please search in Hiroshima Kaira. It's enough to arrive my group. It's okay, Victor. Thank you very much.
Yes.
For everybody.
Yes, thank you, Katsuya. Thank you very much for your nice presentation. And let me check, is there any question? Let me check. I did not find any question. Oh, nice to see you. Let me ask you, for solitons, symmetry of the work is absolutely important. But there are different ways how to create this definite optical symmetry. For example, can you image we create metal-organic framework, for example, and magnetic element. This frame really optically active, and this right space group. But this frame, this lattice is absolutely diamagnetic. We introduced magnetic elements inside inside metal organic frame, magnetic elements, but they are inside the optically active channels. Is it possible to register solitons?
Yes, of course, it is possible, but the intensity of response are completely different. Of course.
Yes. Yes, for sure. But it's possible.
Yeah, it's much bigger, and we can measure also. But the paramagnetic case or diamagnetic case, it is difficult to measure. Only we can measure by optically.
Yes. Katsuya, there are some questions from Roman Morganov. Roman.
Hi, Roman.
Hi, Roman. Roman, where is you?
Roman?
Hi, Katsuya.
Yes. Yes.
Are you okay?
Yes, fine.
Where you are?
Yeah, ask this.
Yeah, interesting.
Yeah.
How to distinguish soliton and domain wall?
Bit loud voice, please.
Hello?
What is your question?
My question is how to distinguish solitons and domain walls in ferromagnet.
Ferromagnet? Yes, we are working in a ferromagnet, but we don't have the anti-ferromagnet.
Please
we are very interested in insulating magnet.
It doesn't matter, insulator or conductive.
Sorry, your voice is too small.
Really?
Yes, Roman, yes. Your voice is a little bit with noise. So maybe be close to the microphone.
Okay.
Much better.
Can you hear me?
Now, okay.
Now, okay. Good. First question, how to distinguish soliton and domain walls existing in any ferromagnet?
Yeah. This is completely different. Yes. The Magnon case is you need a perfect crystal, for instance.
But
our case is we don't need a perfect crystal. Very dirty crystal is also possible to use. The soliton is very, very robust. But the Magnon, they are stopped at defect. Then this is completely different with the Magnon case and the chiral case. Before we are talking with Roman about the Magnon case. The resonance is very similar with the Magnon case, but our finally findings are completely different with Magnon.
No, I mean not Magnon, I mean domain wall. Domain
wall is also different, yes.
But if you look at a picture of block domain wall, you will find absolutely same picture as yours.
If you consider about the domain wall, this domain wall is 360-degree domain wall, right? The pitch is 660 degrees. Is it possible? 360 degree domain wall.
So okay. This is just block domain wall.
No, domain wall is also they are never move as smoothly.
Okay, but second question. In your crystals, domain walls exist or not? They contribute to the magnetic properties or not?
Yes, it's at a very low field. It is possible to see hysteresis. And if we make a dirty crystal, for instance, a powder sample, we can find a hysteresis. This case, our sample in powder sample, there exists domain wall of magnet, a magnetic domain wall.
But soliton contribute to hysteresis or not? Your soliton.
Single crystal is no hysteresis. Yes.
Okay.
Thank you.
I'm very sorry, dear colleagues. The time was running out. Thank you, Katsuya, again for your nice presentation. Thank you.
Thank you very much.
Thank you, see you. So, dear colleagues, our next speaker is Svyatoslav Tolstikov. Svyatoslav is assistant professor at International Tomography Center. The title of his presentation is the following: Pyridyl-substituted nitroxides in design of Magnetoactive system. Please, Svyatoslav, it's your time.
Oh, hello, everyone. Just a minute. Куда вожать? Там видно что-нибудь? А так? Sorry. Как она? Yes. Видно?
Yes. Yes. Your presentation is in front of us.
Слава, сделай на весь экран просто, да и все.
Sorry.
Отлично.
Dear colleagues, let me present my work. More than 20 years ago, Professor Paul Ray with co-workers have published the first example of unusual magnetic behavior of copper nitroxide complex. It was tetranuclear copper complex with a meta-pyridyl-substituted nitrile nitroxide, which undergoes structural rearrangement accompanied with spin transition and 110 Kelvin. Later, we decided to modify that nitroxide by wearing off a substitute at fourth position of pyridine cycle and introducing of a methyl group to this position shows the promise of our assumption, and the first polymeric chain complex with hexafluoroacetylcettonate copper which undergoes a reversible spin transition at approximately room temperature with a color change was obtained. After that, we have synthesized a library of ligands with different types of volumes and different types of volumes of substituents at fourth position of pyridine cycle. And in my presentation, I will talk only about nitronil nitroxides. Its reaction with copper gave a variety of molecular, dinuclear, and tetranuclear complexes, and polymeric chain heterospin complexes with analogous for all compounds binuclear cyclic fragment. I will start from polymeric chain complexes with which obtained for the following nitroxides. Solid phase consists of centrosymmetric binuclear fragments bonded by copper bischelates into polymeric chain. When the cooling heating cycles are repeated at temperature in range from 5 to 350 Kelvin, a reversible spin transition takes place. The transition occurs because of structural rearrangement in centrosymmetric fragments. The main transformation of structure associated with a change in direction of Young-Taylor axis in a square by pyramidal environment of copper. So in case of compounds with ethyl and propyl substituted nitrogen nitroxides, the structural rearrangement is realized in more complicated way through the doubling of crystallographically independent part of structure, so that the fragments become asymmetric and fragments of this copper bisphalates. And the two dimers linked by this fragment remain centrosymmetric, but upon cooling, the shortening of copper nitroxide distances in these dimers occurs in different way. For example, in complex with ethyl substituted nitronyl nitroxide, the copper distances equal to at 250 Kelvin to 2.2 angstrom, and upon cooling to lower temperatures in one of the dimers, the distance remains almost unchanged, while in the other it is reduced. Then with cooling, the distances continue to gradually decrease, and at low temperature become almost equal, about to angstrom. In the chain with propyl substituted nitronyl nitroxide is the blue line here. After doubling of the cell, the copper nitroxide distances in dimers change dramatically. In one, it's even increases, and in the other, it reduces. And the second dimer, the character of exchange directions changes from ferromagnetic to anti-ferromagnetic, which causes on a sharp drop in magnetic moment near 200 Kelvin. Below this temperature, an increase of magnetic moment is associated with rotation of ferromagnetic exchange interaction as the first dimer due to the significant copper oxygen of nitroxide distances. The transitions for other complexes looks unfinished at room temperature, cannot be reached maximum because of its thermal instability above 360 Kelvin. For all complexes, thermochromic effects is observed, and in case of cyclohexyl and pyridyl-substituted nitronyl nitroxide, there is no cyclic fragments, and the chains are built due to the coordinations of ligand with copper through the nitrogen atom of pyridyl ring and the oxygen atom of nitroxide group, or through the nitrogen atoms of pyridine rings. The cyclic dinuclear complexes was obtained for the with the following ligands. The crystal structure formed with centrosymmetric dinuclear molecules in which the paramagnetic ligand performs a bridging function linking to copper fragments. In case of complexes with these substituents, no significant structural rearrangements were recorded, while the temperature was varied. The increasing of magnetic moment value at low temperature suggests the ferromagnetic exchange interactions between the spins of the paramagnetic centers. Cooling the complexes with phenyl and thiophenyl substituent ligands leads to the structural rearrangement, like we saw in cyclic fragments in polymeric complexes. Oxygen atom of nitroxide changed its position from axial to equatorial, and copper nitroxide distance are reduced to almost 2 angstrom. Because of this, the nature of interaction between paramagnetic centers changes from weak ferromagnetic to strong anti-ferromagnetic. And we see here thermochromic effect too, like in polymeric chain complexes. For the complexes, for the ligands with etoxy and butyl substituents, these groups are so mobile, and for complexes with etoxy substituents, these complexes exist in form of 2 polymorphic modifications, and in case of butyl substituent, we have 4 polymorphic modifications, and we have no any magnetic measurements, because it's always forms in mixture of phases, so we cannot do it. In case of isocanaline nitroxide, after many attempts of synthesis, there was obtained 2 complexes with solvate molecules. In this structure with dichloromethane, also 2 molecules with different geometries of the coordination environment of copper atoms are crystallographically independent. In one of them, the copper oxygen nitroxide distance is 2.3, and in the other 1.9. So for the first molecule, we can assume the presence of weak ferromagnetic interactions and exchange clusters, and for second, a strong anti-ferromagnetic one. In tetrahydrofuran solvate, the short copper nitroxide distance already at room temperature, and magnetic behavior suggests strong anti-ferromagnetic interaction between paramagnetic centers. The cyclic binuclear fragments and molecular complexes of tetranuclear complexes structure has a similar structure, and in which oxygen atom of nitroxide group, which not involved in binuclear fragment, is bonded to an additional fragment of copper or copper with ligand. The most interesting complex was obtained with ethyl-substituted nitroxide. Despite the fact that the complex has analogous to mentioned above complexes structure at room temperature, investigation of the magnetic properties revealed a non-trivial temperature dependence of the magnetic moment. The value of magnetic moment at 300 Kelvin is about 3.7 magneton bore, and during the first cooling cycle, practically does not change to a temperature about 230, after which it sharply decreases, reaching 0.9 magneton bore, about 90 Kelvin. With further cooling, a slight decrease of magnetic moment by 0.3 magneton bore is observed, and in the region, and the monotonic, and then there is a monotonic decrease to 1.3 at 5 Kelvin. Upon subsequent heating, magnetic moment gradually increased. A slight increase is observed in the range about 100 Kelvin, and a sharp increase occurs above 270 Kelvin, reaching after that initial values. During the next cooling, the magnetic moment remains practically unchanged up to 220 Kelvin, after which it begins to decrease, reaching a small plateau at 1.7 magneton Bohr, below 150 Kelvin. Compared with the first cooling, decrease of magnetic moments in this region 150 to 220 occurs more smoothly, and the amplitude of change is smaller, while a sharp decrease in magnetic moments in region of 65 and 85 Kelvin persists, and its amplitude increases. Below 65 Kelvin, the value of magnetic moment is 0.7, and slightly decrease with further cooling. If we take a single crystal with a mass of 2.25 milligram and do the same measurements, we will see that the temperature dependence of these magnetic moments similar to a polycrystalline sample. During the repetition of the cooling heating cycles, irreversible changes in magnetic properties occur. After 20 cycles, hysteresis clearly manifested in low temperature region. If the initial polycrystalline sample is grounded in matter, the dependence of magnetic moments is relatively close to that for polycrystalline sample after repeated cooling heating cycles for several times. The main difference is the value at low temperatures. This value corresponds to a content of non-interacting paramagnetic centers, about 30%. To explain the non-trivial magnetic behavior, we made many attempts to study its structure at different temperature. Gradual decrease in temperature from room temperature to 220 Kelvin does not lead a significant change in structure, but further cooling to 150 provoke the crystal crashes. Due to the fact that the crystal was coated with a layer of epoxy resin, the fragment remained held in a shape close to the original crystal. This made it possible to resolve the structure. It was found that the transformation of structure below the phase transition point leads to change of elongated axis oxygen in copper biparamedic, change in position of ethyl group, change in pacanyl molecules, and copper distances decreases by more than 1 angstrom, and the intermolecular distances between atoms, oxygen atoms of nitroxides, elongates by 0.5 angstrom. In subsequent experiments upon cooling several crystals of complex with liquid nitrogen and subsequent heating to the higher than 300 Kelvin. For one of the fragments, it was possible to obtain X-ray structure experimental data. The results of these experiments show that the crystal structure of these samples corresponds to low to the data from previously experimental at 150 Kelvin. In this case,
Svyatoslav, excuse me, 1 minute.
1 minute.
And you have to finish.
Okay. So many structural experiments shows that in order to achieve a complete transition from the high temperature phase to a low temperature phase, the crystals must be cooled to lower than 100 Kelvin. And for the reverse, they must heat it for at least to 350 Kelvin. And we made some experiments of IR and EPR spectroscopy, and the main, and we can say that upon heating there could be a formation of an intermediate phase on asymmetric structure when the in diameter of copper in diameter 1 copper nitroxide pair is coupled. So this provoke structural crashes and magnetic behavior.
Okay, thank you, Svyatoslav. Only one question from Professor Bukhnov.
Svyatoslav, thank you very much for your interesting presentation. I have seen that you observed different polymorphic modifications, especially in the case of normal butyl-substituted pyridine.
Yes.
I want to ask, does they convert one into another? The main difference between them is the position of alkyl chains. I think it should be not a large barrier between the modification. Does they convert one to another?
We don't know. We didn't do this these experiments. I cannot say that they can. Probably they can change their modification. So we didn't do any experimental.
I understood. Thank you.
This.
Okay, thank you, Svyatoslav. Dear colleagues, just escape. In case I follow the list of questions and there are special chat, you can write your question in chat and receive from your colleague any answer. And now we have the last presentation from our sponsor, from Cryo-Trade Engineering. I have to say that Cryo-Trade Engineering company specializes in the supply of cryogenic equipment of its own production, as well as the waste domestic and foreign manufacturers. The company's employees would like to present their results, but before the presentation that will be given by Andrey Omirov, let me ask Sergey Weber to say a few words about Cryo-Trade Engineering. Please, Sergey.
Viktor, thank you. Just as organizer, I would like to say, first of all, thanks to Cryo-Trade Engineering for the agreement to help us with preparing this conference. And second, just mention our collaboration with this company. With their help, we manage helium purification, and also we collaborate in the case of PPR spectroscopy. They develop for us a cryogenic system, and Andrey, please tell about your research and about your equipment you developed. Thank you.
Thank you, Sergey. Andrey, please, it's your time. Please.
Thank you, Victor. Do you hear me? Okay, nice. Hello, colleagues. My name is Andrey Omirov. I am from Cryogenic Engineering, and I will tell you about some equipment that we supply in Russian market. My presentation will have two parts. First of all, I will tell about foreign equipment that we supply in Russian market, and the second part will be about our equipment that we produced in our factory. So I will try to tell very short about us. We work in the Russian market already more than 10 years. And for this moment, we finished already more than 1,000 projects. Already we created about 100 cryostats that installed in all Russia and like Belarus, Kazakhstan. For this moment, we placed in Moscow in our territory with square about 750 meters, square meters. You can see some photo of our territory. We produced the cryostats, some transfer lines, and another cryogenic equipment, and also we are the distributor of a lot of different companies. You can see here some logo of our foreign partners. I want to tell that for this, that from the February of this year, we become the distributor of quantum design cryogenic equipment. It is our win, I think. It is equipment that known all of us, I believe. Our main equipment is cryogenic equipment, and we are the distributors of such companies like Cryomech and Sumitomo Heavy Industries. We provide different cryogenic refrigerators, generators of liquid nitrogen, liquid helium liquefiers, and something like this. Also, we can produce some vacuum insulated transfer line for liquid helium and liquid nitrogen, some accessories and consumables for this. About quantum design, I believe that all of us know about this company. The main products of this company is PPMS and MPMS. First system of quantum design is MPMS. It is a split magnetometer. They developed, if I'm not mistaken, at 1984, and from 2007 years, they offers third generation of this equipment. PPMS and some of their version like Inoue and Versalab offered from 1994. And for this moment, it is the second generation of PPMS, and also the new equipment like the Inoue. It is a fully dry system without any liquid helium. Also, quantum design provides such equipment like optical. It is split optical split magnet with 7 Tesla field and very lot sample space, very big sample space volume. It have diameter about 90 millimeters, and it haven't another analog in world market. Also, quantum design have a daughter company, Montana Instruments, that provide some ultra-low vibration cryostats. Montana Instruments models S50, S100, S200. They have different sample chamber, and the main parameters that haven't analog in the market is peak-to-peak vibration, like 5, 15, and 20 nanometers. Another interesting equipment that we offers in our market, it is a dilution cryostat from Blue Force. It is the standard in ultra-low temperature area, and equipment from Atacube. It is some cryostats integrated in optical table. It is some piezo positioners. It is some analytical equipment. If it will be interesting, I can tell you about it later if you have any questions. Want to set about such interesting equipment like Chase Cryogenics. It is some stages that you can install on your standard cold head that have at least 100 milliwatts at 4.2 Kelvin. You will need to create another radiation shield and vacuum shower, but you will have temperature like 1 Kelvin or 0.3 Kelvin or 0.1 Kelvin in case of dilution stage. We also can provide full cryostat with this stage. And also we already have experience, you can see it on the right photo, that in creating 1 Kelvin cryostat without a pumping system, without helium-3, only with helium-4. Want to set about Zurich Instruments. They provide lock-in amplifiers and impedance analyzer, but it is more interesting for this conference. They provide equipment for work with qubits and quantum computer control system. It is some AWG generators. It is system for ready answer from qubits quantum analyzer. It is a system for PQSC. It is a module for assembly the system, and also they have new system SHFQA that can work with up to 64 qubits without PQSC and another equipment. We provide equipment. We provide superconducting magnets. We work with cryomagnetics instruments. It is American factory. They provide a lot of different magnets up to 18 Tesla and speed coils up to 9 Tesla. Also, we have our own production of cryomagnets. You can see on the right photos our own magnet for 9 Tesla, and we can produce dry system up to 10 Tesla magnet and wet system up to 14 Tesla. There is some slides about analytical equipment from Atacube, but I'm sorry, I'm not a specialist on this area, so I can't give you a lot of information about it. Lakeshore Cryogenics, it is the big supplier of probe station, VSM system, whole system, and sensors, and another equipment like this. Not important. The second part is about our own production, and the about this will set my colleague, Chief Engineer Max Klonov. So Max, please.
Thank you, Andrey. Thank you. Hello, everybody, and thank you for the opportunity to present our products on this very interesting conference. So let me start from the, in the beginning, I would like to say that the strongest point of our company from my point of view, and the main point is that we can produce cryostats from scratch, and not only from scratch, but for special treatments of experiments. We are having like a standard line of products, but we can do any cryostat which you need. If it's possible to do, we will do it. We are doing it from the start, from the tight connection with the experiment, with the customer, to understand totally the task of the customer. And after that, we are in collaboration with the customer. We are producing a technical technical description of the task of equipment. And after that, we are starting R&D process to produce, finally to produce a system which is meeting totally expectations of the customer. That is, I think, it's most strong point of our company in terms of the production possibilities. And here on a slide, you can see brief line of cryostats we produced before. Like you can see, it's like interesting challenges which we met in the past, and which we met in the past, and you can see this is a huge rupture machine to test samples, to test mechanical properties of the samples. It can rupture the sample in low temperature conditions. This one is providing nitrogen, liquid nitrogen temperature here. It's closed cycle. There is no liquid nitrogen here. It's two cooled heads here. And we are providing the sample temperature lower than 70 Kelvin. This one is a rather big vacuum chamber with liquid helium temperature staging inside of it. It's dry system too. There is no liquid cryogens at all in this system. It's all based on closed cycle. It's two cold heads down here at the chamber, and inside you can see the air shield, which is covering the whole inner space from radiation heat load. And inside you can see the huge stage, which is cooled by down to 4K. And next slide, please, Andrey. Thank you. And here you can see I can say very small part of the cryostats we built before. And we chosen here systems which are designed for some magnetic applications. Most of them are for magnetic applications. This one is a liquid helium cryostats with sample in a helium vapor. It's a flow-in cryostat. There is no vessel here. You just put in transfer line and put inside liquid helium to cool down the sample zone. And sample is just put it inside in a sample tube to be cooled down. And this one was made for Kerensky Institute, and it was made especially to be installed in a magnet of the customer. So we met his terms, of the geometry of this cryostat to fit it in his system. And also you can see the optical access ports here. So this one is just for magneto-optical investigations. Second one is closed cycle cryostat for magnetic applications, which we built especially to install in our own previously produced closed cycle magnet with a magnetic field 6 Tesla. And here you can see the construction, which is allowing customer to bring cryostat closer to a magnet and put it down to the room temperature bore of the cryostat. Here you can see the outer shield of the cryostat. It's not non-magnetic, it's from pure aluminium. And inside it's a system with heat exchange gas. So you can you are having a heat exchanger tube in which you insert the long rod with a sample mounted down here. So you can put it in a magnet in the central point of the magnetic field and to make some magnetic measurements of the properties of the sample. This one is just like a example of a totally customized cryostat, because in the upper side you can see it's our standard low budget liquid nitrogen cryostat, but in the bottom you can see a totally customized optical head, because customer needed to cool down huge plates of ceramic samples. So we designed totally new sample holder for that and designed totally new optical shield. Here is the cryostat we made for our colleagues from International Tomographic Center. It's a system to convert to make conversion of the ortho hydrogen to parahydrogen, to provide, as I understood from the customer's explanation, to provide gas environment for MRI tomography for the applications. Here you can see our our pride and joy. It's a cryostat for EPR spectroscopy, which we made in a very tight collaboration with our colleagues from International Tomographic Center from Inoue, with Sergei Weber, which helps a lot to us to make this cryostat as fitted for the application as it possible for us. And we are very, very grateful to Sergei for his patience and for his income in design of this product. So thank you very much, Sergei. And second last cryostat is, this one is a very interesting system, very difficult, and was challengeable for us. It's a closed cycle system with a 10 Tesla magnet. It was a challenge for us to build up 10 Tesla because it's a combination of the two superconducting wires. It's a niobium titanium and niobium freestone combination. It was very tricky to make this magnet actually, and it's integrated with exchange gas sample tube, which is cooled down with a third third loop of the helium. It's like, you can see here is a cold head, and here you can see the vacuum pump and the helium system, which is providing cycling of helium inside of the cryostat with throttling of it, and this is allowing one to achieve a temperature down to 1.6 K on a sample with a very small heat capacity for sure. So 1.7, 1.6 one can reach if application is with very low heat load. If heat load is more, so you can reach higher temperature. But actually, one can reach 1.6 in this system. And here is a system. It's a magnetic cryostat, just sample, rather simple cryostat with a closed cycle, which can be put down, up and down in a magnet system. And for this one, we recently made optical access renovation. The customer asked us to build up optical access shield for him, and we totally redesigned bottom side of the cryostat. So actually, it's like this was like just to explain you that we can do a lot of types of equipment, and we can do it from scratch. We can do it from a technical specification from a customer, and we like to understand task of the scientist, to be on one page with the scientist, to understand what he needs, and just to collaborate with the scientist to bring best solution. That's the main point of my speech actually. So I think thank you very much for your attention, and thanks again for Sergey for his support in our job.
Thank you. Dear Cryogenic engineering team, you are our colleague. I would like to thank you for your time, for your interesting presentation. You are really every time ready to collaborate with researchers, and we are thankful for your support. Thank you.
Thank you very much.
Thank you.
Dear colleagues, we finished our session. Let me thank again all our speakers and all our participants for your kind attention. Now we have coffee break. We meet again in 20 minutes at 1 p.m. Moscow time. Thank you, everybody. See you in 20 minutes.
Thank you. Thank you very much.
Thank you very much.
Thank you.